Hello, my name is Ansh, and today I'm here to teach you the Maclaurin series. This is a topic in A-level further maths that many students tend to struggle with, but it's actually not that hard. It's just because the formulas in the formula booklet look a bit complicated that a lot of people do get tripped up. But today I'll teach you exactly what it is, when you can use it, and how to answer the generic Maclaurin series questions as well. So without any further ado, let's get straight into it. So, firstly, what is the Maclaurin series? Well, as it turns out, sometimes it's helpful to take an expression that you know, for example, sine x, right, and express it as a series of terms. In this case, the expansion for sine x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial and so on and so forth, right? And that's all Maclaurin series is trying to do. It's just trying to take a function, right, and it's trying to expand that function into a series of terms. So the actual definition of how you get to the Maclaurin expansion is if you have a function f of x, then its Maclaurin's expansion is going to be f of 0 plus x times f dash of 0 plus x squared over 2 factorial times, sorry, this is meant to be an f dash dash of 0, and so on. So do you see how we got the sine expansion? So sine of 0, right? Which is just nothing. So you don't get the term. And then x times sine, the differentiation of sine is cos 0, right? Which is just x times 1, which is x, which is the first term. And essentially every time it's going to be sine, which is going to be the double dash, it's 0. Hence why the next term is cubed, and then the next term is to the 5, the next term will be to the power of 7, and so on and so forth. Okay, so now you might be thinking, oh great, so we can just expand every function under the sun. Well, that's just not true. There has to be three conditions that need to be met in order to expand these functions. So the first condition is that f of x can be expanded into a convergent series of terms. For those of you that have forgotten what convergent means, there's two types of functions. There's divergent functions, like this one here, right? That just keeps on going and going and going and going, and it probably keeps on going till infinity. Or sometimes it keeps on going till negative infinity, depending on where it's pointing to. But what we're interested in is the second function, or the second type of function, which converges. All it means by converging is that it's essentially getting closer and closer and closer and closer to a certain finite value, right? So it's getting closer to in this case, this finite value is probably like 1.6 something something something. I'm not too sure exactly what it is, but it's converging to that value. So hypothetically, you could find the Maclaurin series, or not hypothetically, actually, you could find the Maclaurin series expansion for this function. So the second condition in what functions can be expanded into series of terms is that each of the terms in the function must be able to be differentiated. Well, for example, in case you've forgotten what differentiation is, the differentiation of this would be 3x squared plus 2x, right? So as you can see, everything can be differentiated there, so you could expand this out into series terms. Well, this one is already expanded out into series terms, but you get my point. And the last condition, and this is the last of the three conditions that are necessary in order for a function to be expanded. So the last condition is that each one of the terms that you differentiate, including the initial term, whenever you set the value of x to 0, it has to lead to a finite value. So for example, if you have a function ln x, right, and you want to expand this out, well, it fails to meet this criteria, as when x equals 0, ln x is not defined, right? You can try that on your calculator now. So the ln of 0 is not defined. Actually, it's not defined or infinity. But either way, you can't find the Maclaurin's expansion of ln of x because the differentiated terms, or the initial term in this case, when you set the value of x to 0, it does not have a finite value. Well, now that you know what functions you can and can't expand, the good thing is there's only generally two types of questions that they ask you in the exam to do with Maclaurin series, right? And the reason at the start of the video I said that this is not a particularly hard topic is because you're literally given most of these expansions, like in your formula booklet for A level further. So you can literally just look at it. If you have e to the x you need to expand, you can look at this expansion and literally jot it down without proofing. And in fact, you don't even have to prove any of the assumptions that I told you earlier, although they are good for understanding. So you might be asking me, what are the two types of questions that I keep or that I have mentioned, right? The first is questions that ask you to just use the formula. So there's going to be a question with like a compound function, and these are questions that I go through later on in the video. So there's going to be a question with a compound function, and it'll just ask you to expand it until like 4 non-zero terms or 3 non-zero terms, right? So you'll use these expansion, you'll use one of these formula, two of these formula, put them together, and then have a result. The second type of question will require you to use the general formula. It will give you a function, and instead of using one of these predetermined formulas, it will require you to figure out the expansion by differentiating the function over and over again and setting it to 0, right? So basically the second one is do it yourself type of expansion. And there can be variations of both these styles of questions, some more challenging than others. But just to make sure you really understand how to attempt these, let's go through a couple of expansions together. So this is a very generic A-level further maths question where it's like use the Maclaurin expansion for 1 plus x to the n. Well, we're actually given the formula for that in the formula booklet under binomial expansions, right? To find the first three terms for fx and a function. So they won't directly ask you to just do the expansion for like 1 plus x to the power of 2 because that'd be too easy. So what they do is they manipulate the expression somehow, or they compound it to make it a little bit more challenging. But as you can see, this can be just written as 1 plus minus x to the power of minus 2, right? And that just means that we can use this expansion, right? And instead of n equals minus 2 and x equals minus x basically, and just plug it in. So the first three terms in this case will be 1. Let's do the answer here. The first three terms will be 1 plus minus 2 minus x, right? And then plus minus 2 minus 3 to x squared, right? This just gives us 1 plus 2x plus 3x squared, and so on and so forth. Actually, this particular series, it just goes 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4, and so on and so forth. But as you can see, really, really straightforward. You're given the expansion in the formula booklet. You manipulate the equation somehow, fit it to the equation that's given to you, and work out the solution. A slightly more tricky, actually a much more tricky example of this question is expanding sine x and the square root of 1 plus x. Well, the good thing is we've just seen 1 plus x, so it should be fresh in your memories. But as a reminder, this is nothing but sine x, basically, times 1 over the square root of 1 plus x, right? So we can look at both of these terms, sine x and 1 over the square root of 1 plus x, differently. To save you the pain of watching me do this live, right? To go through things a little bit quicker, because this is for the sake of your understanding. I've got this pre-expanded right here up until the x5 term. Well, we do a very similar sort of thing that we did here, essentially, right? Where we manipulate it and we say, oh, it's just to the power of minus a half. And every time you see n, you put the power of minus a half in, right? And we already know what the expansion for sine x is, literally given to you in the formula booklet. X cubed over 3 factorial minus x5 over 5 factorial. So now that we know that the individual expansions for sine x and the individual expansion for 1 over the square root of 1 plus x, we can literally just times the two together to get the expanded series. And remember, the question only asked for until the power of x to 5, right? So we times both the expansions together, and this is again a very common trope. For more compounded formulas, you might have to times two Maclaurin's expansions and three Maclaurin's expansions with each other to find like the general term of the equation, right? So obviously, because we're only looking for terms up to x to the power of 5, right? You can do x times 1 times minus a half x times this, times this, times this. But if you times x by x to the power of 5, you'll get x to the power of 6. So you weren't times it. The last time you times it was x to the power of 4, right? And you'll get these terms. Then you times the x cubed by 1, because that keeps you within 5, by x within 5, by x squared, that keeps you within 5 as well. So you get 3 terms. Lastly, you time the x to the power of 5 term just with 1, because if you times it by x again, you end up getting x to the power of 6. So this is sort of them multiplied with each other, but the question will generally sort of limit how many terms you need to find. So in this case, we only need to find terms up till x to the power of 5. You further simplify that, gets you the answer, which is x minus a half x squared plus 5 over 24x cubed minus 11 over 48x to the 4 plus 421 over 1920x to the 5. Cool. Now, this third example is do-it-yourself one. So now we've done two sort of, where you just plug in the formulas and find up to a certain term. But in this case, we'll do it the other way, where you use the general formula. You have to differentiate first, and then use the general Maclaurin expansion formula to get the first four terms. So f of x is e to the x cos x, which means if you differentiate it once, it's going to be e to the x cos x minus e to the x sin x. Well, this just gives you e to the x, right, cos x minus sin x. Differentiate it again to get e to the x cos x minus sin x minus sin x minus cos x. Well, this is just e to the x, or actually e to the x minus 2 sin x. Or you could write it as minus 2 e to the x sin x as well. This is minus 2 e to the x sin x plus cos x. And f4 dash would be minus 2 e to the x. Actually, you could simplify this into minus 4 e to the x cos x, as sin x and minus sin x cancel out. Cool. So now that we have the first four differentiations of this, right? Just as a reminder, the Maclaurin's expansion for f of x is f of 0 plus x f dash of 0 plus x squared over 2 factorial f dash dash of 0 and so on and so forth, right? So what we'll do first is we'll get the very first term we differentiated, right? Set that to 0. Then we'll set x times the next differentiated term to 0. So if you remember the next differentiated term, everything here simplified to 0. Then we'll set x squared over 2 factorial next term to 0, and so on and so forth, right? Well, once you actually calculate all of that, you'll be left with something like this. And then you just simplify it properly. Make sure you're counting the minuses and stuff, because sometimes it can be minus minus, and it's a very further mathsy mistake to make, where you do the hard part right, but then you do something like 2 times 3 and you get 5 or something, right? So especially with Maclaurin series expansions, or if you're substituting it in, make sure you really do your working out. Try to do as little as you can in your head. That just means that it's harder for you to mess up. But the answer for this question turns out to be 1 plus x minus x cubed over 3 minus x to the 4 over 6. Okay. This was pretty much all you need to know for Maclaurin series for A-level further maths. I hope you found this video helpful. Please do let me know if you'd like me to cover any specific topics or questions. Email me. My email's in the description below. And also let me know what style of videos you prefer. Do you prefer it when I don't do the working out live, so that it's quicker for you to learn and understand maybe? Or would you prefer like sort of seeing my thought process and seeing me struggle, especially doing these more challenging problems live? Anyway, leave your thoughts in the comments below. I'll see you on the next one. Thank you very much for watching.